let's go right away in the next talk with Christian Paquin. He's a Paquin, pardon. Christian Paquin. He's a crypto specialist in Microsoft Research Security and Cryptography team. He's currently involved in projects related to post-quantum cryptography, such as the Open Quantum Safe project. He's also leading the development of the U-Proof technology. He is also interested in privacy-enhancing technologies, smart cloud encryption, and the intersection of AI and security. Prior to joining Microsoft in 2008, he was the chief security engineer at Credentica, a crypto developer at Silanis Technology, working on digital signature systems, and a security engineer at Zero Knowledge Systems, working on Tor-like systems. So give a good round of applause again for Christian Paquin on his talk on Stay Quantum Safe, Future-Proofing Encrypted Secrets.
All right, hello everybody. It's good to be back virtually in Montreal. I'm a Montreal native and a native French speaker, so if you detect some accent, that's the reason. So today, we are staying COVID-19 safe by doing this virtually, which is a great idea. And I will explain how to stay quantum safe as well. And the goal of the presentation is to explain how to future-proof our encryption systems to defend against the quantum computer. So as it was said, my name is Christian, and I work for Microsoft Research. Well, since I like to talk about me, let me talk a little bit more about me. We've all been hearing about quantum computers lately. They're all over the news. Well, in fact, I've been hearing about this for a long time. I was a young student here at the University of Montreal almost 25 years ago, and that's where we studied quantum cryptography and trying to build these new things that promise to revolutionize the world of cryptography and computing. After that, I joined a more practical side of the industry. I became a crypto engineer, worked for many years until I landed a little bit more than 10 years ago at Microsoft. And I'm currently in the crypto and security team, where at MSR, where we work on cutting edge cryptography, things that will end up in products in 5 to 10 years. And our current focus is post-quantum cryptography, which is the subject of this talk. I was here last year at NorthSec to present on the subject. So the goal of this year's presentation is to give an update on what happened in the field and what can be done to start migrating our systems to post-quantum cryptography. We've heard about the quantum revolution and the promises that this magical computer will have on the field of computing. Using the special properties of quantum mechanics, computers that built with such properties could magically calculate all sorts of parallel computations at the same time, resulting in algorithms that are impossible to implement on normal classical computers. So there's a lot of R&D around the globe on this, trying to realize the vision of this quantum computer. In fact, I have some colleagues at MSR that are building both the actual physical stack, the quantum gates, and I have some other colleagues building quantum software. You can download a QKD, a quantum development kit for Visual Studio, and start programming in Q# to implement these quantum algorithms. So now they could be just now they would be simulated on a normal computer, but as soon as we can plug in one of these quantum computer, the same software would work. So for all of you aspiring quantum hackers, and that you should start to learn these things now. So one big problem for the field of security is that quantum computers completely break our existing cryptography. Indeed, in 1994, Peter Shor developed his famous algorithm that allows to factor and find a discrete logarithm of large numbers. So essentially breaking the RSA and ECDSA algorithms. That also it's valid for Diffie-Hellman and the elliptic curve variance. There's also another famous algorithm called the Grover algorithm that breaks some symmetric primitives such as hash functions and block ciphers like AES, but not in a catastrophic way. It improves the attack, and by simply doubling these primitives, we're able to resist the quantum computer. So this is less of an issue. But for asymmetric primitives, like asymmetric encryption and signatures, it's a terrible result, and essentially breaks most of the protocols we use on the internet today. So you can say bye to your HTTPS TLS connections and your SSH connections to your servers, your certificates, your update channels that are using signed messages, your private communications like Signal, and even your Bitcoins, all gone if a quantum computer is built. And there's different opinions on when will this be implemented. Some say 5 years, some say never, or a longer time. But there's a big consensus around a quite serious possibility that these could appear within a decade or two. And being security practitioners, we have to take this kind of worst case scenario in mind in order to migrate to a quantum safe cryptography. That is changing our base algorithms to rely on problems that we don't know how to break with a quantum computer. And one question is, why would we want to do that now? Why can't we wait in 10, 15 years? Like we handled Y2K, if you're old enough to remember. Just do it the year before and panic and we'll be safe. Well, the problem is that the data that we exchange today on the internet is at risk because it can be captured and decrypted later with the help of a quantum computer. So if you have long-lived data, data that has a long-lived threat model and needs to be secure for multiple years, you have to take that into consideration. Another point is that these cryptographic algorithms are used in protocols like TLS, SSH, etc. And these take a long time to update. They are designed by committees, and we need to define new extensions and agree on them so that they can be used in an interoperable fashion on the internet. And also, new quantum safe algorithms would behave differently than the RSAs and the DSAs that we know. Some could have longer keys and message signature sizes. They could take longer to run. And we don't even know if the code that we want to modify is easily modifiable. When we transition from MD5 to SHA-1 to SHA-2, we found a lot of horror stories in some code bases where these things were so hard-coded that update was difficult. So when you run the clock backward, taking into account your threat model time and the time it would take to change the infrastructure, you get a date of when you need to start this transition. And for many use cases, this date could very well be yesterday. Fortunately, cryptographers are on top of this. NIST, which is the National Institute of Standards and Technology, this US body that dictates the crypto primitives used by the US government. It is also a de facto standard organization for the world because most of the NIST standards are adopted around the globe. So they, in 2017, they made a call for a new set of algorithms that could resist quantum computers. And we're at the beginning of last year, they went into a round 2 where the 69 proposal in a Thanos type fashion got reduced to a smaller subset of these, 26 remaining, and some of them got merged together. And we are now just at we're expecting very soon this summer the announcement of a round 3 survivors of all these algorithms. So we expect a smaller list, and in 2 to 4 years, we're expecting new draft standards that would make these algorithms standards and available for the industry. So the question for us now, who are dealing with integrating algorithms or have protocols and services that use cryptography, is how can we get ready And more importantly, what about the data that works today? Should we ignore these few years, or can we do something today to mitigate the quantum risk? Well, there's many things can be done today, and that's what I'm going to discuss in this presentation. So we joined this open source project called the Open Quantum Safe project, where we offer a framework integrating multiple quantum algorithms from the NIST competition. And this allows us to make some experiments and study them in various environments. So as you can see from the list here, it's a big industry and academic collaboration project. It's led by the University of Waterloo. And we've integrated the OpenSSL library into different applications in TLS, SSH, and VPN, for example, through forks from the popular boring SSL, OpenSSL projects and OpenSSH and OpenVPN. We also have some wrappers in different languages. If you're interested to use OQS in C++ or C#, Go, Java, or Python, we have these wrappers available as well. So the openquantumsafe.org project allows you to get all these links and to learn more about the project. So the main thing I'd like to discuss today are the result of two studies we did using the OQS project. The first one deals with integrating this post-quantum cryptography in TLS and SSH. So we wanted to see what would be the impact of changing these algorithms, and specifically how to integrate it in a hybrid scenario. I'll discuss that in a second, what that means. So we did that. I'll talk now about the results in OpenSSL and OpenSSH for TLS and SSH. So a hybrid scenario essentially mixes both a classical algorithm with a post-quantum one. The trust we get with crypto algorithms comes with time. The reason we believe this in the security of RSA is because it's been a long time. It's been around since 1976. A lot of people tried to break it, and nobody was able to. Not until a quantum computer comes around. These new post-quantum proposals, some of them are very new. So even if we don't know how to break it with a quantum computer today, it doesn't mean that we won't be able to do it in 10 years. In fact, we could break it with a normal classical computer. We don't even know. So one strategy is to try to get the best of both worlds, to combine the security of our classical scheme, let's say RSA or ECDHE, and combine it with a post-quantum one. And the resulting key that we use on the wire is secure if any one of them is secure. These protocols, when you do a TLS connection, you don't use your ECDHE or RSA key directly to encrypt the message. You use it to derive a secure and quick, fast, symmetric encryption key, like an AES key that you use to do your encryption of each packet. So we would do the same in the hybrid fashion and have both classical and a post-quantum input to the key derivation function to result in the AES key that would be based on the security of both schemes. So fortunately, we're able in TLS and SSH to negotiate algorithms, but we don't have the ability to negotiate two different algorithms and use them in conjunction. So the paper explores different ways to do that. One way is to just invent a new scheme. Instead of saying I'm going to use ECDHE and I'm going to use Psych together, Psych is a post-quantum algorithm, I'm going to use a new algorithm called ECDHE Psych. And for the TLS layer, it's completely oblivious to the fact that under the cover in the crypto layer, we're separating these two things and doing both ECDHE and Psych computations in parallel and combining the results. So it's a great approach that it's easy to implement without changing the protocol or the implementation, but it's doesn't give you a lot of flexibility for negotiating different variants. And alternatively, we could define new hybrid approaches that requires changes to the protocol through extensions. When you consider all these options, you have to think about the compatibility, backward compatibility, performance, latency. You don't want to introduce new data flows, new messages. You don't want to break old hardware implementing TLS protocol, for example. So for our implementation, we use the naive approach, the first one, where we define new combo algorithms to allow us to do a quick implementation without changing anything in the protocol. So we were able to integrate in the key share TLS 1.3 extension. I'm just going to concentrate on TLS 1.3. We also had some code in TLS 1.2, but kind of forward-looking, let's talk about TLS 1.3. So the results were quite positive. Some crypto algorithms are a bit too big to fit in the TLS, which has limits on the public key and signature sizes. And OpenSSL, its implementation, also constrains things further down. But by modifying the code, we're able to fit most of our integrations, our algorithms, and I'll discuss that in a second. And we're able to use this OpenSSL modified version of OpenSSL to stand up Nginx and Apache servers to test our modified clients as well. This GitHub link here, that's also, everything's available from the open source openquantumsafe.org project that I showed at the beginning. Just shows you that if you know how to use OpenSSL, then you can use it exactly the same way to stand up a test client and server with these new post-quantum hybrid algorithms, in this case, Frodo and ECDHE with the P256 NIST curve, and using ECDSA and QTesla hybrid certificate there. And then you get the connection, everything works as expected. We also had another part of the paper was to discuss SSH. SSH is kind of more the same, so I'll skip over it. It's another key exchange protocol with authentication, and we're able to provide both hybrid classical and post-quantum key exchange and authentication as well. And again, if you're aware of how to use SSH, you'll notice that we can use it in exactly the same way. You can take our fork and install it on a server and start connecting to it using hybrid post-quantum security. So the interesting thing about what we observe, as I said, is that most quantum algorithms were able to be integrated. Some of them with the yellow check mark just means that we had to modify some of the code in OpenSSL to allow bigger structures. That was just a implementation choice of the OpenSSL designers to limit that. And some scheme, for example, NTS, which is a code base version, use a very large artifacts in there that we were not able to fit them. But for most of them, it was okay. For signatures, a lot of signatures use quite big artifacts as well. Keys are signatures, and we had to modify the OpenSSL and OpenSSH code to make it work. And very few of the algorithms we tested were not able to fit. So Picnic, for example, Picnic version 1, the higher level 3 and 5 wouldn't fit. But in the second round, Picnic 2 version, they did modify the algorithm, and we were able to fit them in TLS. And only the Rainbow signature algorithm, we were not able to fit it in the SSH code base. So very positive. Overall, these new schemes fit well into our target protocols, TLS and SSH. The other thing we wanted to consider was benchmarking. So how efficient these algorithms would be in real life. In the second paper, we designed two experiments. The first one, we use the network emulator as part of the Linux kernel to connect two virtual Ethernet endpoints. One, a client using the OpenSSL S-Time, connecting to a server that was that we instantiated with Nginx. And the nice thing about the network emulator is that you're able to change its behavior. So we added different runtime, different distance between these two endpoints, and also changed the packet loss probability from 0 to 20% in multiple clicks. So I apologize, the screen is very small. The point is not to see the details of each result, but just to show the trend. And what we observe is that for most algorithms on good networks, the performance was quite good. We compared the state-of-the-art ECDHC connection algorithm with a hybrid version of itself with 3 different post-quantum algorithms. And most of them had very similar performance. And what we observe is that for algorithms with larger keys, for example, then they would have to be split across multiple packets when they would be to be fragmented. And if the packet loss probability is higher than 5%, then there's a good chance that some data would need to be resent, and that would slow things down for these algorithms. So yeah, so overall, good news and good simulation for the usage of hybrid exchanges compared to the pure ECDHC. The second result, we tried to emulate something, not emulate, the first one did the emulation, but the second one, we tried to simulate real-life conditions by having a client in virtual machine connected to 4 different virtual machines across the planet in different data centers, and trying to retrieve various size web pages from 1K to 10 to 100 to 100K to 1 megabyte. And some surveys we looked at put the average web size to 2 to 3 megabytes. So having a 1 megabyte limit gave us a good approximation. And so not surprisingly, when we try to fetch these different pages across these different VMs, we notice that, of course, the further away you're connecting to and the larger the web page, connection slows down. But what's interesting is that ECDHC with ECDSA certificate its performance is not that much better than the same thing in a hybrid combination with a post-quantum algorithm as things gets further away and with bigger web pages. So the more we look with real-life conditions, the amortized cost of adding this extra layer of post-quantum security does not penalize you too much, which is good news for if you want to try to deploy these technologies today and start experimenting with them. So you get a lot of protection, basically a safety net against quantum computers for the data that's exchanged today, for a very adequate performance cost. So these are good news for experimenters and deployers. So the last project I'd like to discuss today is the VPN tunnel that we played with. So we have an integration into OpenVPN through our OpenSSL fork, because OpenVPN bases security on TLS. And this is a nice scenario for both legacy applications and for clients that would be difficult to update, like IoT devices that have a long lifespan. So it would be hard to magically transform all these devices and clients to make them quantum secure. So one way to do this is to leave them untouched and simply add a post-quantum tunnel and tunnel their communication through it. So you get the quantum safety automatically without having to change what's going on the wire. And we experimented with this approach in a real life scenario. So there's one of our sister team at Microsoft Research is working on Project Natick, which is an underwater data center module that floats, or not floats, but is in the ocean on the North Sea of Scotland. And the reason to experiment with these is that it brings data closer to the customer, and there's some inherent cooling benefits to be in the water like this. And we ran a post-quantum VPN to it from our Redmond headquarters, and just with normal rekeying and everything. And we ran this for a long time. The details are in this URL here. And what's interesting is that this experiment kind of gave us confidence that we're ready to start experimenting with post-quantum deployments with real life data. So this is a test data center, so it's not real customer data. So we're kind of we're allowed to experiment with this without putting anybody in danger. And also, as you can see, the little seal on the water there, that picture was taken from a webcam outside the data center. It's not easy to send a technician down there to fix something. And the fact that we're able to do this experiment gives us confidence that the techniques we use could be replicated in normal data centers. So that brings us to the end of this presentation. And I hope that you got the message that quantum computers are coming, and that's the safe standpoint to take as if you work in security and cryptography, because the costs would be high if you're wrong and don't expect them. And there are things we can do today to protect the data that's on the wire this instant. And we need to start thinking about transitioning to quantum safe. There's a few things that we can do today before we wait for new standards. And I hope that the various projects that I presented give you a good start. And we're always happy to hear some feedback, get some contribution in these open source projects, either a photographer, a practitioner, or an enthusiast like to integrate these things in your projects. So please feel free to communicate with me if you have some questions or suggestions. Thank you very much.
Okay, so let's go with the first question. Will Microsoft support the winner of round 3 in its mainstream products? When? Most popular only, or even some legacy, but still supported OS?
I can speak on behalf of the Microsoft product teams, which will have their own decision making in there. But I just assume that that Microsoft will follow the industry. In fact, we have my colleagues at MSR. We have 4 of these schemes in the competition. So of course we have like our favorites, and we're experimenting with these more than some others. But the Microsoft servers and teams and Edge, which is based now on Chrome, would just work in collaboration with the industry to pick the winners. I know Google did some experiments and with Cloudflare, and then we'll see what emerges there.
Yeah, it's tricky.
But yeah. Microsoft Vision. Oh, go ahead.
Do quantum computing break perfect forward secrecy as well? PFS?
So yes. So I mentioned a lot of RSA and ECDHE. So RSA is not perfect secrecy. You break it once, and you can break all the history of the communication that was done with that key. ECDHE uses just ephemeral diffeomment, elliptic curve diffeomment. You need to break every renegotiation with it. But if you store it today, you can. If you have access to a quantum computer later, you can break any of these rekeying. So yes, it breaks it.
Okay, good. Bitcoin question. You say Shaw's algorithm is a threat to Bitcoin. Doesn't it apply only to signature verification of new transactions, but Merkle tree remains immutable?
Well, so, I mean, wherever you use, I know that some Bitcoins uses the, was it DSA or ECDSA? I forget, I'm not a Bitcoin expert, but it's whatever that part, that part will be broken. And I'm not sure what's the impact on the Merkle tree per se, but one thing I would say is that there's a different threat model for key exchanges and encryption and signatures. So encryption, like the key exchange you get in TLS to define a secret that you'll use to encrypt the session, that you can record and decrypt later. For authentication, the attacks are more online. So you need to convince somebody that you have to forge a signature, you need a quantum computer now. You cannot backbreak an authentication that happened 20 years ago or 10 years ago. So you would be able to forge it, but it's been signed with a timestamp. So what's at risk today that you need to migrate first is everything that uses encryption, asymmetric encryption. And the signatures, we have a bit more time. So don't want to scare all the Bitcoin crowd. I put that on purpose, this logo, just to freak out people. But the risk is will come a bit later.
Yeah, they still have time to cash out. Okay, how many qubits are needed to run algorithm to break RSA? IBM's claiming they can reach 53. Yeah,
so it's going to be a lot more. But right now we're a bit in a situation where before the invention of the transistor, the computers, they were use big light bulbs and they would break and everything. So it was inconceivable that you could build larger algorithms with this technology until somebody invented the transistor, and then everything got smaller, faster, and you were able to scale up quite fast. So we're waiting for a breakthrough like this in quantum computing. And look, my colleagues at Microsoft were working on this specifically, not using the type of physical systems that implement the qubit that, for example, IBM has been using. My colleagues are working on something called the topological computer that would be more stable and scale better according to their research. So if they're able to build this, that's kind of all taken into consideration in the various estimates that are floating around. It's really hard to predict. It's just we're expecting a breakthrough to happen within a decade that will allow us to build these things.
Okay.
So these 50, you would need millions of qubits to build current algorithms, and it's doubtful that the current technologies used today would be able to, by themselves, be able to scale up to that level.
Okay, we'll do one last question. Okay, have you looked at WireGuard's capabilities for post-quantum encryption? It might be more relevant than OpenVPN in the future.
Yes, so I have not personally. I know that some people did. I saw a recent paper, I forget by whom, that I think they were implementing post-quantum into WireGuard. The reason we did OpenVPN because it was almost free, because they use OpenSSL, so we just plugged in our fork in there, and with little modification we were able to do that. So some people has been looking at that, and I don't think it would end up in OQS if they contributed at some point, but I think if you just search for that, you might get, if you're interested in the details, you can look it up, like WireGuard post-quantum.
Or if you want to post the paper too in the Twitch chat, that'd be great as well, if you can find it.
Yeah, we'll have to do the same and search for it. I don't know. It might be unpublished results. I think we just discussed that with some colleagues. Yeah.
Okay. Well, thank you very much, Christian. We're out of time. We'll give you a big round of virtual applause. It was really great to have you again at NorthSec. Before moving out of the Twitch stream, because my colleague Flo is going to take the next moderator spot, I would like that we give a big round of applause to our AV guys. I'm just gonna post their Twitch handle in the Twitch stream, just because everybody said that what they're doing is awesome. They've been working for like a week on this. I know they're gonna probably thank them again later, but I don't know. It's just nice to recognize their work right now and later as well. And well, see you in 10 minutes for another talk.